Hey guys, welcome to my channel. So in this video we're gonna learn how to count the number of set bits in a number. So we're gonna look at two different methods to do this. One is gonna be more efficient than the other. Now let's just jump right into the description of set bits, right? So what are set bits? Now it's very simple. Every single time there is one in the arrangement of the bits of a number, it's called set. It's a set bit. So this is a set bit, this is a set bit, you get the point, right? So we're gonna just find or try to compile a program that is gonna count these set bits in a number. So let's look at the first approach we have in our hand. So in this function we're declaring a count variable, and while n is not 0, we're going to increment the count every single time n is an odd number, right? Or we can also represent this as every single time the rightmost bit of n is set. So, and then we're going to just right shift n by 1. So we just right shift the arrangement of n by 1. So we get like the rightmost bit or set bit one step closer. So step by step we kind of reach to a point that we have counted every single set bit. So we're gonna implement this in the compiler and we're gonna learn it. But before that, let's try to go to the whiteboard and understand what we're doing, right? So let's take a number called, not called, but let's take a number 5. And the bit arrangement of this would be this: 0, 1, 0, 1, right? So in this process, what we're doing is we're basically checking. So by the way, one tip: if you want to check if the rightmost bit of a number is set or set or not, you can just AND the number with 1, and that's how you'll get it, right? Because in 1, every single bit is 0 except the last bit. So if you do the AND with it, you can just see if the last bit is set or not, right? Very, very simple trick. Now, by the way, if you're not understanding these, just check out my bit operators video. I've explained right shift and left shift and all the operators briefly there, so just check it. Now, so every single time we're doing the AND with 1, so AND with 1. Now, if this bit is set, we're just going to increment the counter. So in the first case, this bit is set. And then what we're going to do is we're just going to right shift it, right? So after right shifting this, what is it going to become? It's going to become this: 0, 0, 1, 0, right? So this just got deleted, and this pattern right here repeated itself. Not there, sorry. Repeated itself in here, right? So then we're just going to check if this bit is set or not, which it isn't, by ANDing with 1 again. And we're not going to increment the counter this time. And next time we're also going to right shift it. So it's going to become this: 0, 0, 0, and 1. And this time is actually set in the most extreme right. So we're just going to increment the counter again, and we'll have the answer as 2. So, and by the way, after we right shift this, because we're going to right shift it anyways, because we have it in our function, it's going to become 0, right? So we delete this last bit, and it's just going to be 0, 0, 0, 0, and we don't have anything left. So that's how we terminate the loop. So, very simple. Now let's undertake the process of actually coding this. So let's declare the counting variable or the count variable as 0, and we're gonna code the loop while n is greater than 0, or we can just do while n. And what we're gonna do is we're gonna AND n with 1 to check if the rightmost bit is set or not. So count plus equals. So only increment the count if the last bit is set, right? Sorry, AND with 1. And now we're also gonna right shift it by 1. So step by step, we're going to come closer to n being 0. And by the way, this is also dividing n by 2 as well, so that's what right shifting n does. Now at the end, we're just going to return count. Simple. So let's check if it's working or not. So let's print out count of 5, let's say, and let's run it. And it should give us 2, and it did. Let's do 7 and 3. Yeah, it's working perfectly fine. Now this is well and good, but let's check out a more efficient and time optimized algorithm, right? We call this the Kernighan's algorithm, and both of them are essentially log n. The first one is theta of log n, but this one is actual log n, right? So what do we do in this? It is very similar to the last one, but instead of ANDing with 1, we AND n with 1 less than n. So we AND n and n minus 1. And why do we do that? So let's check out the code first. So we declare the variable as 0, we declare a count variable, simple. We have the same loop as long as n remains, so as long as it's more than 0. And then we increment the counter right away. We don't check for any condition, we just increment the counter. And what do we do next is, what this line is doing is it's ANDing. N is basically the AND of n and n minus 1. What this does is, it unsets the rightmost bit of n, right? And then we get one step closer to n being 0. So now let me come to the whiteboard again and explain it to you, right? Let's clear everything. So let's take 5 again, right? So 5, the bit n is 5, and this representation would be 0, 0. I mean not 0, 1, and this, right? This is the binary representation of 5. Now n minus 1 would be 4, and the binary representation would be this. Simple, right? Now if we AND these two, what do we get? We get this. So it doesn't matter what number we get, that is really not relevant. But what do we understand in here? This was 5 before. You see there was this bit, this bit in 5. Now n is this right now, and this bit is gone. So the rightmost bit is gone in one step, right? And now in the next step, this bit will be gone because we'll just AND it with n minus 1, because n right now, but by the way, this is the binary representation of 4, so n would be changed to 4, right? And then we're gonna do 4 and 3, because n minus 1 will be 3 then, and then let's see what it will become. So 3 is binary representation would be this 1, 1. And now we don't have anything actually, everything is going to be 0 because there is no 1, 1. And it has reached 0 now, so we increase the counter 1 time and then again 2 times. Then we have 2 as the answer again. But yeah, but we didn't like kind of right shift it unnecessarily, because they were like, we would do this because there was a 0, so we kind of saved that step. So I hope you got the point. We're basically unsetting the rightmost bit by ANDing n with n minus 1. That is just a property we know, and then we just incrementing the counter, because n is at least going to be 1, right? And right, so there is at least going to be one set bit. So that's why we're just increasing the counter. And then we do this until n reaches 0, and then we just terminate the process. So now let's code it up, right? That's what we do. So these are gonna remain the same. We're just gonna change a little bit of the inner loop, right? So n would become n and with n minus 1 in each step, and we're just gonna increment the counter. In each step, we're not even gonna look for any condition, and this is gonna give you the same answer. So let's check. The count 7 would be 3 again. It is. And let's do it for 5. sorry, 5 would be 2 again. So yeah, I mean, that was it, guys. So if you learned anything in this video, feel free to like this video and share this with your friends. And today we learned how to count set bits and what set bits are actually, and also looked at why one method is more efficient than the other. And you also learned that if you AND n with n minus 1, you're gonna unset the rightmost bit. So again, have a great day and subscribe to my channel. Thank you.